4, let omega in Rn be a bounded connected open set of class C0. Let omega n be a sequence of bounded connected open sets of class 0 containing omega be a decreasing sequence of connected open sets containing omega and such that omega closure equals intersection n equals 1 to infinity omega n closure. Let lambda 1 of omega denote the first eigenvalue of delta with homogeneous Dirichlet boundary condition. Let lambda 1 of omega n denote the first eigen etc. in omega. So, okay, and here it is in omega n with homogeneous Dirichlet boundary conditions. Show that lambda 1 of omega equals limit n tending to infinity lambda 1 of omega n. So, solution. So, omega n plus 1 is contained in omega n for all n. So, this implies that lambda 1 of omega n is less than or equal to lambda 1 of omega n plus 1. Also, omega is contained in omega n for all n, and therefore, this implies that lambda 1 of omega n is less than or equal to lambda 1 of omega. These two come from the monotonicity with respect to the domain of the eigenvalues of the Laplacian. Okay. So, this implies that lambda 1 of omega n is a monotonically increasing sequence and bounded by lambda 1 of omega, and therefore, we have that limit n tending to infinity lambda 1 of omega n exists. This is nothing but the soup of over n lambda 1 of omega n, and that is less than or equal to lambda 1 of omega. Okay, so that is the initial thing about. Okay, so let un in h10 omega n be an eigenfunction for lambda 1 omega n and integral on omega n un square equal to 1. Okay. So, then un tilde extension by 0 belongs to h10 of omega 1, which is the biggest of these sets, and also you have integral on omega 1 grad un tilde square equals integral on omega n mod grad un square, and that is equal to lambda 1 of omega n, and you have integral on omega 1 of mod un tilde square dx, and that is equal to integral on omega n mod un square dx, and that is equal to 1. So, this is of course bounded by lambda 1 of omega. So, this implies that un tilde is a bounded sequence in h1 0 of omega 1. Therefore, there exists a subsequence such that unk tilde converges to some z in h1 0 omega 1 weakly, and therefore by the relic theorem this goes to z in L2 of omega 1, and this is relic. Okay, and for the further subsequence, which we will choose as the subsequence in question, that un tilde k converges to z pointwise almost everywhere. Because it converges in L2, you can have a further subsequence which converges pointwise almost everywhere, and we will look at that particular subsequence where all these three things hold together. So, this all in L2 of omega 1. Okay. So, in particular, integral on omega 1 mod z square dx equal to 1. So, let x belong to omega 1 minus omega bar. Therefore, there exists a nx such that for all n greater or equal to nx, you have x does not belong to omega n closure, because if it does, because it is a decreasing sequence, then it must happen at some time, because x is not in omega closure, which is the intersection. Okay. Therefore, this implies that un of x equal to 0, because it is not un tilde of x is equal to 0 for all n greater or equal to n of x. And since un tilde nk converges to z pointwise, so this implies that z of x equal to 0 almost everywhere, x in omega 1 minus omega bar. So, you have omega 1 here and you have omega bar which is here, and therefore, it is a h1 0 function in the whole space which is 0 all over this place, and this implies that z belongs to h1 0 of omega. So, lambda 1 of omega is therefore less than or equal to, and so mod grad z square dx on omega. Okay. So, this is because you have integral z square is equal to 1, and therefore, the Rayleigh quotient characterization tells you that the first eigenvalue is smaller than this, and therefore, this is equal to integral on omega 1 grad z square also, because outside omega bar everything is 0, and therefore, this is equal to this, and therefore, that is less than or equal to, by the weak lower semi-continuity, grad of un tilde nk square dx, and that we know is lambda 1 of omega nk. Wait a minute. Lim inf nk tending to infinity, integral on omega 1 grad un k tilde square dx, which is equal to, therefore, lim inf nk tending to infinity lambda 1 of omega nk, as we have already observed, because, and that is less than or equal to lim sup of nk tending to infinity lambda 1 of omega nk, and that is of course less than lambda 1 of omega. So, you have lambda 1 of omega on either side, lim inf and lim sup are there. Therefore, this implies that limit nk tending to infinity lambda 1 of omega nk equals lambda 1 of omega. But we already know that lambda 1 of omega n is convergent, and we have a subsequence converging to lambda 1 of omega, and therefore, this implies that limit n tending to infinity lambda 1 of omega n is lambda 1 of omega. So, with this we will wind up this chapter, and we will now start next time a study of semi groups of operators and their applications to evolution equations.